Oopsie doodle. Okay, so hi people from YouTube if you're watching us later. I've been talking for 20 minutes and I forgot to record. We have been talking about question 3b from the most recent mock qual, but there's a solution to this question written on the solution overleaf file. So everything that I've said so far, I just drew this nice picture where I drew the picture for what's going on, and then I'm going through the proof, and then I talked about the tube lemma, and now you're caught up. Okay, cool. Let's just pretend that I talked to YouTube for a second. Okay, cool. So that's the tube lemma, and we just used it, hopefully to great effect, to get this open subset Y, which are W, this open subset W, which contains X, and then from here, the idea, at least if I go back to my original picture, is that this green neighborhood that I want in X, well, that's just gonna be the W that I get from this tube, right? So then the claim is that X is an element of W. This part we actually know, like it's stated out here from the property, right? The tube lemma gave us that X is contained in W, but the point is that it's also contained in the complement of this set here. Right? So, like I said, this first part is clear. The second part is the only part that you might want to say a couple sentences. So, to show this, we're going to let little w and capital W be arbitrary. Thus, W comma Y is not in D. Or, sorry. No, if I say not in D, okay, it's not in C. For all Y and Y. But this means that f of W is not an element of D. I feel like that is not maybe as clear as it should be. Maybe I should have written more words here. I don't know. Are people convinced by this, or would you like to see more on this sentence? Okay, I saw one visible shrug. Right, so I guess that the idea here is that right, so I guess in particular, I could say in particular, W comma f of W is in C, right? But W comma f of W is not in Z intersect X cross B. So W comma f of W is not in X cross D, right? It's in the first component, but it's not in the intersection. So that means that it's not in the second component. And that implies that f of W is not in D. Right? Thus, X is not an element of F inverse, sorry, not X, W is not an element of X inverse of D. And so X cross F inverse of D is open as desired. And that completes it. Any questions, comments, concerns, or complaints? So I guess I'm going to assign as homework, prove the tooth lemma. Okay. It's not as hard as you think. It's one of those proofs where at every step you do the only thing you can do. Maybe I should add that to the exercises to know document. I just prove the tooth lemma. By the way, I did update the exercises to no document, just with 2 exercises, both in part A, the points and topology part. This first one here that I added is 12. We've talked about this one a lot in our discussion, right? If you have a continuous bijection from a compact set to a Hausdorff set, then you actually have a homeomorphism, right? You know, and you should be able to prove this, but the real reason that number 12 is on this list is because this is just a fact that you should be comfortable seeing and referencing and knowing, right? Because it's quite nice to not have to deal with showing that the inverse is continuous. And then 13 actually comes from something that Anthony brought up on Tuesday when he asked why for this Lie group question, why these components were open. Okay, so 13 states that a space is locally connected is exactly the same as saying that every component is open. Right? The proof of this is actually pretty nice. If you're locally connected, then every point is contained in an open connected set, but connected sets have to be contained in components, right? So that open connected neighborhood is contained in the component, and that means that the component is an open set because I just found an open neighborhood between my point and the set that I wanted to show that was open. And then the reverse, for every point, you take an arbitrary open neighborhood, you intersect it with its component, and then you get a connected open set, which is contained in the original neighborhood. So this proof is pretty easy to do, but it's quite nice because manifolds are always locally connected and lots of spaces are always locally connected. And so this is just a nice bit. And this shows why Anthony's, this emphasizes Anthony's counterexample from Tuesday when he talked about the components of the rationals being non-open sets. Q is not locally connected, as it turns out. So anyway, these are both in here, and we basically talked about both of these exercises. They're mostly just in here for the benefit of future people studying for the topology qualifying exam.
Oh, Jacob, while we're there, in number 2 in the algebraic topology, I just remembered that So I know what the chi's mean from Schultz's notes, but what does the triangle with the K mean in the those that thing?
Yeah, that is the set of K simplices. So the way to read this sentence is that the number of K simplices of L is equal to n times the number of K simplices in K.
Okay, so like you have a complex with all the simplices like glued together. And so if you look at just like the K dimensional ones, like those have to match up.
Yeah.
Okay.
Yeah, so for like a 3 simplex, the 2 simplices are just all of the faces.
Hey, Jacob.
Yeah.
Sorry, Catherine, did he finish answering your question?
I think so. Go ahead.
Okay, so I don't know if you covered this on Tuesday or last week. I wasn't able to attend, but the email you sent out with the comments from Schultz, um, did you talk about those things in particular? I think he says something about yeah, I mean, if did you talk about those?
I did not. So feel free to ask questions.
Could we talk about those things in particular? Sorry, let me pull it up. Jacob. Uh eh, I don't know where your email was.
I have it up on the shared screen.
Oh, okay. Yeah, uh so in one, when he's talking about the results on fundamental groups of graphs, including in maximal trees, elements of finite order, um, can we review that? I think so. I know that the answer to are there elements of finite order in the groups that are fundamental groups of graphs? The answer is no, other than the identity by Nielsen Schreier.
Mhm.
But then I'm not sure what he means the description in terms of maximal trees.
Yeah, so what Schultz means by this is that if you find a maximal tree and you identify that maximal tree to a point, right? So you can deformation retract any tree to a single point,
Yeah.
right? So you take a graph, you find a maximal tree, you deformation retract that to a point,
Mhm.
and what you're left with is a wedge of circles.
Right.
And that's and that's one way to find the fundamental group of a graph,
Okay.
right? And then you just count the number of circles that you
Right.
and you get the free group on that many generators, right? For me, I prefer for graphs because then I just have to count, right? The fact that for a finite graph, G, right? The fundamental group of G is isomorphic to the free group on 1 minus the Euler characteristic of G generators.
Yeah, that requires you to remember what the Euler characteristic is. So,
You know, for a graph, it's either edges minus vertices or it's vertices minus edges. So I always back solve because I remember this and I go, okay, this is supposed to have 1 generator. That doesn't help me because edges minus vertices. So that means that this has 0 generators. So which direction of edges minus vertices or vertices minus edges gives me the number 1?
fair. Yeah,
Oh,
I think
it's vertices minus edges, and then that's how I remember that the Euler
yeah, I was
characteristic
trying to figure out like
vertices
what he
minus
meant,
edges.
and I think that's definitely the way that I like to think about it because I was thinking like, if I have a like I was thinking about like, oh, if you have like 3 circles chained together, right, one after another. Well, by Nielsen Schreier, I know that this probably ought to be like a wedge of 3 circles. I can see that, oh yeah, I can pull one back and I can get the wedge of three circles. So this has fundamental group Z3, or sorry, Z star Z. And alternatively, you could see this as a subgroup of free on two generators by picking the correct paths, the correct loops. So yeah, I think that's definitely helpful. Thanks.
You're talking about question 5, right?
I'm not
Of
sure.
mock qual 4?
I haven't done the mock qual yet. I was out of town this
Oh,
weekend.
okay.
I was just thinking about like that email.
Well, then I'm sorry if I spoiled question 3B for you. But it's okay.
No, there's a good chance that I wouldn't have attempted this question. But it would have been it's good to know how to, like, I've not got a note saying I need to refresh the tube lemma.
Yeah, but my goal with these mock quals is to like slowly ramp up the difficulty of the mock quals. I think that this qual is probably, especially part C, is harder than I would expect the actual qual to be. Because when I wrote out my solutions for part C, all of them were really long. But yeah, so
All right, Jacob, could you just draw like a quick picture for number 2? I just want to make sure I'm getting these definitions correct. That number 2 on the exercises to know the algebraic topology part.
okay, exercises. Yeah. Okay. So this was Schultz's cryptic email. Did I send you all his follow-up email? Okay. I
What do you
feel
mean
like that.
email?
Okay, that is something. Okay, so Dan then asked again, is it important to know the axioms and results for singular homology in chapter 6 on top of simplicial homology in chapter 5? I assume he's talking about 6 and 5 of Hatcher, and Schultz said yes, it is. So there you go. That's the entire email chain. Right. Yeah, Schultz is a boss. Because Dan emailed, and then Schultz just CC'd me in his reply to make sure that everybody got it, that there was a fair playing field to everybody. I'm just like, man, Schultz is great. Cool. So now you've seen the entire email chain. He just said yes, it is. Okay. So exercises to know. Let me move it over here so that I can see what I'm talking about. You want a picture of number 2. So for example, so let's see. So here's a simplicial complex. And I'm just going to take a bow tie. And let's take a 2-sheeted covering of this bow tie. Okay. And if I'm going to do a correct 2-sheeted covering of this bow tie, then I better have 10 vertices. Let's see, is there a way that I can make a connected 2-sheeted cover? I want to say no. Well, I guess that this is the trivial example here.
A connected 2-sheeted cover of this, I think, exists because I remember in Hatcher, because I wanted to say like, oh no, connected two-sheeted covers of certain graphs don't work. And then it turns out Hatcher has like a big table of all the ways that line of reasoning could go horribly wrong. And you could have tons of are like very bizarre covers like that aren't the things you'd think of at first.
Yeah.
Can I make a guess as to what it is, just for funsies?
Yeah, normally when I think of like a two-sheeted cover of a circle, right, I draw like, oh, sorry, if the wedge of two circles, I draw this, right? This is a two-sheeted cover where going once this way is an entire loop this way. Same as going backwards down the bottom, right? Backwards down the bottom this way is also a loop this way in the same orientation. And then these two loops on the edge just correspond to the right side, right? So that's what I normally think of as a two-sheeted cover, right? Every point here has a neighborhood of 2 points.
So doesn't that work for that as well?
So if we try it, then this is a simplex, or maybe it's a simplex like this.
What if you just take out that bottom triangle? Then, because don't those have like too many edges?
Right. Yeah, so if I do something like this.
Yeah, like that should work because it's just turning the picture on the right into like simplices, possibly by.
It doesn't work because if I do this, this projects down to a single edge instead of an entire loop, right?
Why can't you why can't you choose the projection so that that edge becomes an entire loop?
Right. So what I could do maybe is I could do something like this. And then here I could do something like this. And then that makes this work as a graph, right? So if I'm just looking at this like a graph, right, where the interior here is empty, right, then this certainly works. But if I wanted to make this a lift where the interiors also lift, then this wouldn't work. Right? Because then this isn't a simplicial complex. I'd have to add a bunch of edges on the inside in order to turn these into triangles, right, to get a simplicial decomposition. And then I'd have too many edges again, right?
Okay.
Yeah. But I guess here's an example with in fact, I'll even label this just to make it clear. This is a one complex. So i.e. it's a graph.
Also, so what is the exercise number for this?
This is exercise 2 in part B for exercises to know.
Okay. Could you just write that on there? Sorry.
Yeah, absolutely. That way when people look at this. So let's do exercises to know B2.
Thanks.
Yeah, I think that's another thing that I'm going to do with the exercises to know doc. I'm going to do point set topology comma part A, right? Just so that way it's easier to reference these bits. But,
sorry,
yeah,
so with the one complex, can you now do like the double bow tie?
Yeah, this works.
Okay, it's just like homeomorphic to the double bow tie.
So this is a two-sheeted cover. In the same sense that this was a two-sheeted cover. Right. Every point downstairs, let's take a new fun color, let's say purple, right, contains a neighborhood such that the preimage of that neighborhood is two disjoint pancakes. Right. maybe instead of calling this a two-sheeted cover, we should call this like a two-pancake cover.
I guess my
short
question
section.
is, why did you have to turn that middle point, like middle shape in the cover into like a trapezoid?
Yeah, so what am I doing here, right? I'm getting my inspiration from this, okay? So I want to go from here to here, and that needs to represent, okay, I'm gonna erase a color down here just to make the picture easier to see, right? Going from this purple to this purple needs to represent an entire loop, right? So I need to have 3 edges and 2 vertices in that path. So here I have 3 edges and 2 vertices in that path in order to make this quote unquote work. Right? Because the pre-image of a vertex, if I'm going to cover a graph with a graph, should be a vertex. Okay. And then by unique path lifting, the lift of an edge, since this edge is a path between 2 points, right? This edge needs to have a lift for every choice of base point, right? So I need to maintain the number of edges and the number of vertices, or I need to at least be able to write my cover as a simplicial complex that has the right number of vertices. So like for example, I could have like a trivial cover of this here with a circle, which I could draw as just a graph that has 1 vertex and 1 edge. But that's because I can just add in these 2 vertices and I don't change the space. Right? I can just upgrade midpoints of an edge to a vertex, right? And I don't change the space. So yeah. So it could be, and maybe this is something that is a subtlety of this problem that I didn't really think about before now. Yeah, L could be a simplicial complex that has like a bunch of extra vertices on the edges of one cells, right? But you can just get rid of them and then you can get this result. Or maybe you can make sure this happens and you always choose like the minimal simplicial decomposition or something. I don't know. But there is a way, but yeah. Yeah, I don't think that this thing that I said out loud is actually a problem for this question.
Jacob?
Yeah.
So this isn't a question for us to do now, but could you, in addition to the or maybe as part of another qual, include some problems about the things that Schultz mentioned, like results on simplicial homology groups and applications to specific examples and stuff, like just the stuff that he mentioned, just so that like we can look at those.
Okay. I will look into that. To be honest, I got that email. I was just like, oh, okay, sure. But I was just like, for me, when I hear like results of singular homology, the way that Schultz says that, let me look at this, right? It's like results on simplicial homology groups and their applications to specific examples. I don't know. I think of like, this is normal stuff of like using excision for simplicial homology, things like this, right? Because those are the results that he tends to focus on. I'll look through his notes and see if he has any other simplicial homology specific results.
Okay, thanks. That would be great. Yeah, because I wasn't sure. I'm not exactly sure what he means by, yeah, these are like, you know, what you should do. Like, yeah, I know that I need to study the long exact sequence and Meyer victorious, but like, is that all he means?
Same. But I think that it is very reasonable for you to say, Jacob, I'm busy trying to study other problems. You do this part so that way I know what things to study. That's a very reasonable request. So I'm more than happy.
Okay, thank you.
If you're like, also do that while juggling, then I'd be like, no. But I don't know. For me, the most useful thing about this email was it reminded me what the definition of nowhere dense was. Nowhere dense just means you have empty interior. And look at that, his example for 3, he even specifies that n is greater than 1. Good job, Schultz. You don't get a degenerate n equals 1 case. Okay. So the solution that I wrote in the solution doc for question 7 is a little different than the one that I wrote for in the notes from Tuesday. So there are a couple of small corrections. So like if I were to correct the notes from Tuesday, so to correct for number 7 on Tuesday, the function capital F should be a function from m to Rn m plus 1. Because if I am remembering this correctly, and I can double check this, I suppose I can just open up the file and I can look at it. Or even better, right? So this is what I wrote last time, but this thing that I underlined in red on the right, these are bump functions. Their image is not Rm. The image of all of these things is R. Right? So I have n copies of Rm, and then I have n copies of R. Right? And so instead, right, I get n copies of Rm and then n copies of R. So I get n times n plus 1. A lot of the proof is exactly the same. The main difference is that the proof, other than that small correction, the proof that I presented in class on Tuesday, I constructed the partition of unity explicitly so that way I'd have a neighborhood around every point that was constantly equal to 1, that had my partition of unity constantly equal to 1, which made proving that it was an immersion slightly easier. And on the solution document, I just started with any old partition of unity. I didn't construct it. I just took the definition for the partition of unity, which is defined in Lee, which meant that I got to spend a lot less time constructing it, but it did mean that proving that the function was an immersion was harder. So feel free to compare and contrast those and take the solution that you see fit. But I think it was Shanna that specifically asked, hey, I want to know more about partitions of unity. So I decided to write the solution where I just took a partition of unity and I didn't construct it. I just said, put a partition of unity with respect to this cover on the space and then go nuts. So hopefully comparing and contrasting those solutions will be beneficial. And the solution to question 8 looks really long, but that's because it's just it's a lot of small statements that make a long proof. And I think that's all that I'm going to say about the solutions to the mock qual, unless somebody asks me a question about some of these solutions.
This is kind of jumping around a little bit, but so on
Go for it.
exercises to know problem 11, in your solution for like that
From
first,
which part?
oh, sorry, in part A.
Okay.
So in that first bullet point, if I remember correctly, you use like a generalized lifting lemma or general lifting lemma maybe. So I don't have my notes right in front of me, but if I remember correctly, when I was going through it, I was concerned because I think it was Y, I don't think you stated was locally path connected. So I was curious, like, if you can prove that using like what you gave us, or because if I remember correctly, it is like a requirement of that lemma. Does any of that sound familiar?
Wait, so you're saying that this is question 11 from exercises to know part A? Points at
I
topology.
think that's what, oh no, I'm sorry, part B, my bad.
Part
Sorry.
B.
In my head, all the lifting stuff is part A, but it's actually part B on your document, sorry. Maybe that makes more sense.
Yeah, so for part B of question 11, the lift
Wait, sorry,
of
part A, it's just the first bullet.
right, so showing that there exists a fixed point from a circle to R.
Right, so I think I understood like what, like you were using the general lifting lemma,
Wait, sorry,
right?
so which, are we on A or B?
It's
the first
B,
bullet
I'm
point.
sorry.
Right?
So
Yeah,
no,
let's
it's
just
not-
make the.
It's not the circle one, Jacob. It's not that one she said.
Oh, okay. So sorry, algebraic topology. That's what you meant.
Oh, yes, I'm sorry.
Okay, it's great. Okay, so where?
Oh,
Okay,
okay, so it's
this
the
makes a
first-
lot more sense because I was looking at these and I was like, all of these codomains are simply connected. So I don't know how you would lift to something. Okay, but this makes a
Sorry.
lot more sense. Okay, let me read this problem and see what's going on. Path connected some of these. Okay, so that means that they're right. Okay. Okay, I now understand what you are. Okay, so you are asking like, what's the lifting property that I'm using? Because
Do
you
you
have been
use-
studying topology all summer and you know that paths lift in covers, right? But why do other spaces lift? Yeah. So
Like, I think when I was reading the statement of the lemma, I think you were using, it said that, I think it was, I forget in your notation, but like, I think it was Y that had to be locally path connected. But I wasn't sure how we got locally path connected, like from the given information.
oh yeah, I did say path connected. But I probably should have said connected locally path connected spaces. Although, see if I can find where I stole this problem from. Because you have to understand that I don't come up with any problems on my own. I'm not smart enough for that. Where did I put this problem? Is okay. Let's look at this one. Okay, so it looks like that in the original problem, X and Y are supposed to be connected, locally connected, semi-locally, simply connected topological spaces. So there, yeah. So yeah. Part of this is that they are locally connected, but the statement that I was going to say, this is called the lifting lemma, or the lifting criterion, depending on if you're working with generalized function or not. Then if pi, let's see, how do I want to write this? If the image of pi 1 of y comma y naught is a subgroup of the image of pi 1 of x tilde comma x tilde naught, then there exists a lift f tilde, which takes y to x tilde, which is unique up to choice of f tilde of y naught in the pre-image of f of y naught. So writing the diagram, right, I have that the fundamental group of x tilde x naught, this goes down via p star into pi 1 of x comma x naught, and then this goes via f star from pi 1 of y comma y naught. And then this implies, and then you draw the same diagram, except with f's and p's, x and x tilde and y. And there exists an f tilde, right? So the reason why paths always lift in a cover is because the fundamental group of the domain of a path, right, is an interval, right? Because a path is just a continuous function, right? It's an interval 0, 1 into your space. And then if you have a cover, well, the fundamental group of an interval is trivial. So that means that the image of the trivial group is always a subgroup of whatever the image of the fundamental group is through your cover, right? So f star of pi 1 of an interval, right, always satisfies this condition. And so that means that this lift always exists. And this lift is unique up to, and all of this is saying is up to choice of base point. Right. And let me color this bit a different color so that way you can tell that it's separate from the statement. But this is, and I might have written a slightly better version here where I did like a base point dependent one just so that way it could be unique up to base point because I used pointed maps for P and F. But yeah, but this is the lifting criterion or the lifting lemma for cover.
Okay, so does I think it's Y. So does Y here need to be path connected and locally path connected?
So it connected and locally path connected imply globally path connected, right? But I think that you only need to be connected and locally connected, and I think that's fine. But the version of the statement that I gave is connected and locally path connected. And the assumptions that Schultz basically always gives is connected and locally path connected. Because to quote Schultz, why even talk about covers in fundamental groups if you're not connected and locally path connected? So. Once upon a time, I had a copy of Moncrief's, and it was by my desk. And it appears to have vanished. Oh, no, there it is. Okay, so the lifting lemma, this is page 478 of Moncrief's. Although if I remember what this lemma doesn't say, right? So let me write this in red. So on page 477, Munkers imposes that all spaces for the rest of the book are connected and locally path connected. Or I guess not all spaces in covering maps. For the rest of the book are connected locally path connected. So he states the general lifting lemma where he says let P from E to B be a covering map, right? And then he also assumes that Y is path connected and locally path connected. So all of his spaces are connected and locally path connected for all of this story. And I would be absolutely flabbergasted. That's a fun word. If Schultz asked you to apply the lifting property without giving you some connected locally path connected spaces. Right. Or the way that Schultz always phrases it is that it's locally arcwise connected. Right. But that's the same. hopefully that very long-winded explanation at some point answered your question.
Yeah, thank you. I thought maybe with like the locally simply connected and all that, like maybe you could prove locally path connected. And I spent some time like trying to do that. And I think I convinced myself that that was not going to happen. So just wanted to like make sure.
Yeah, let me actually fix that now. Sorry, next time I post an update, it will be correct. Yeah. Connected, locally
But yeah, the thing about, I didn't think about how it generalized. That's really cool. That's like a nice way it all fits together.
Yeah, yeah. This is the version of the lifting criterion that I prefer to memorize, just because if you want path lifting, you just throw a path in for y, and you're like, oh, that satisfies the condition for the path. I don't think that I've seen a question of the qual yet that's asked something about like a circle including into like the wedge of two circles and then asking you to prove something about this, because this map lifts up to the universal cover because the fundamental group of the circle is a subgroup of whatever, or not the universal cover, but this lifts into like this cover. But I don't think that I've seen any questions like that on any of the old quals that I've been looking at while making mock quals. It's almost always like, hey, you have a semi-local, sorry, you just have like a simply connected domain over here, right? You just have like R or something, and then this maps over into something, and then you take the universal cover and then you use nice universal cover. Down. There exists a lift. All right. Any other questions, comments, or concerns from me? Yeah, so I know that Rule requested some problems like the ones that Schultz put in his notes, and I'll spend some time this weekend reading his notes to see if I can find some questions that don't look like things that we've already talked about. But are there any other questions or requests? As you all know, we have only one more meeting of our topology qual prep seminar, which is Tuesday. And I have some extra office hours next week. And you can find that info on the website on the bottom. I just put all the extra office hours in the free extra spot, so it's down there. And if enough people are like, Jacob, have another office hour. So I wasn't planning on having a fifth mock qual, but maybe I'll have like a worksheet or something that I'll put in there if I find some of these extra questions that Raul requested. But I can write another mock qual if you all would find that helpful. Do that.
Oh, I mean, if you don't want to write a full mock qual, just like a worksheet with questions like what Schultz is saying would be helpful, I think.
Yeah, I will try to post at least something else over the weekends. So we all have something else to look at.
Yeah, we were requesting some extra kind of sneaky Seifert Van Kampen problems because we've already kind of memorized some of these. And then, and Katie, let's ask about that Riemann metric. So if you can give us a quick hint before we go.
I feel like I've asked a lot of questions. Does anyone else have? I don't want to take up with another.
Oh, okay.
But I guess Shannon, if you're curious, so what was it? Okay, so it's proving that every smooth manifold admits a Riemann metric. So if I understood the problem correctly, like eventually what you really need is you need like Euclidean space to have that metric. So you can prove that like the dot product is a Riemannian metric. Is that correct?
Right.
Okay, so is it
Yeah.
as simple as like you just plug in the vector fields and then you just say like, well, the components of the vector fields would be smooth. And then if you just like multiply those and add them together, that's still smooth?
So, okay, so this is another use of a partition of unity. So it makes sense that
Yeah.
that you're both been thinking about this because you've been thinking about partition of unity stuff. So you cover your space in charts to Euclidean space. All of these charts are diffeomorphisms, so you can pull back the Riemannian metric on Euclidean space to that chart. Right? This is called a pullback, right? But the way that you compute the distance between 2 points in this chart is you just take their images under the chart and then you compute the distance between those 2 points, right? Over there. So that's how you compute distances locally. And then you need a way to paste these local distance functions into some sort of global distance function. Right? And the way that you do that is by exactly using a partition of unity. Right? You multiply each individual metric that you get on your chart with a bump function defined on that chart. Right? And then you take the sum of all of these local metrics times bump function bits. Right? This sum is defined because a partition of unity says that at every point, the sum, all but a finite number of terms are 0, right? So the sum of this potentially infinite collection of functions is actually well defined at every point, right? And then at every point, you're just taking a finite sum of smooth functions, which is going to be smooth. And that's how you kind of paste this story together. Yeah. And so that's the overall broad way that this thing is done. Right. And then this goes up to the tangent planes in kind of a canonical way, because the charts that you choose, right, you also get up, because since the chart is a diffeomorphism, that means that there's an isomorphism between the tangent planes for Rn and for your manifold. And so like the dot product on your tangent space also just kind of comes over in this nice way. You can get partial credit for that problem from Fred, though. I think I got 4 points for defining the dot product to be 0 everywhere. And then he was just like, dot products are non-degenerate, but then he still gave me like 40% on that problem. And I was like, I'll take it. So. I think that somewhere in Lee, he actually explicitly constructs Riemannian metrics on manifolds using a partition of unity.
Yeah, like I think he even has the proof. Like I think the big picture more or less makes sense to me. I think what I realized I was kind of worried about was that, I mean, I don't even know if Wilhelm would want to see you do this in the problem, but to actually prove that there is a Riemannian metric on Euclidean space. So I just wanted to like prove it, I guess, that the dot product actually did like what the problem said it should do. Which
yes, the right.
All the sources I've looked at seem to think it's like incredibly obvious. So maybe it's very simple.
Okay, so, okay, I wouldn't say that that is incredibly obvious, because if you take the real analysis sequence here, then one of the things that you prove is that like if you have a metric on a space, right? Sorry, if you have a metric on a Hilbert space, it's called, right? If you have a metric on a Hilbert space, then you can use that metric to produce a dot product. Right? And then the harder direction is, if you start with a dot product, can you use that to build a metric? And the answer to that is yes, you can. Right? The real thing to understand is that, like, the normal Euclidean metric and the dot product are the two things are generated by the same thing, right? You can either get the normal dot product on Euclidean space, or you can get the normal Euclidean metric. In either direction, they are the same. And for our purposes, we're just going to take that as a black box that comes from real analysis. We're not going to study Hilbert spaces with enough detail to know how to do this, because that takes a while of real analysis to get to the point where you would want to prove such a thing. And even if I could remember that proof, which I can't, and even like I could Google this proof and talk about it, it is beyond the scope of what we would talk about in topology, right? We're just going to take that Euclidean space has a Riemannian metric because it's Euclidean space. Of course it does. That's fine.
Okay, so I should just assume that, don't worry too much about it, and then like commence with the process you described.
Right. Yeah, I don't mean to like badmouth the people that study analysis, because it's like a super interesting field, but like, you know, we're topologists. We want like the squiggly wiggly stuff, not like the rigid Euclidean stuff, right? It's okay. I understand that most of the people who are taking the topology qual are not going to become topologists. That is okay.
If nobody else has questions, I have another, but
So since it is 9:54,
yeah, I'll let
what
you
I'm
go.
gonna, so you can ask me another question after this, but there are some people who might be interested in going. So I'm gonna go ahead and stop the recording. So goodbye if you were joining us from YouTube. Where's the button? I'm a professional.